Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll wrap up Chapter 10 on automated model selection for multiple regression. I have written a function that allows us to put everything together, all the different criteria for model selection, and it's called f.bestSubset. I've defined it as a function. It takes a formula, a data set, and how many best models of a certain size will it report back. So I load the library leaps in this function, and I do the reg subsets, and we're going to do an exhaustive search, meaning we're going to look at all possible models if we can, and then we're going to bind as columns all the possible output. So we're going to have which variables are included in the model, how many variables are in the model, what the residual sums of squares is, and then some of the criteria that we looked at, R squared, adjusted R squared, Mallow's CP, as well as the BIC statistic. And we'll put all that into BS2, and we'll make sure that we have the appropriate column names on there, and then I muck around a little bit to make sure I label the columns appropriately, and then I sort the models by the best BIC value. Had to pick something, just decided to pick that one. And then I return BS2, which is the model selection best subset model selection value. So I'm going to show you what this looks like in a moment. So here I'm going to run this function with this formula. So I have to wrap this formula in the function formula, and then specify the data set, and by default it does 5 best models for every size. And then it ends up not fitting on the page here. I have a couple columns that wrap down here, so I'm going to just hop over to R where we can see all the columns. So this is the output for the Indian dataset. It's sorted by BIC, so we have the lowest BIC first. We want to minimize BIC, so this is the best model here at the top, and then the BIC increases from there. The other statistics basically do the same thing, but not exactly, right? So the CP statistic starts small, we want to minimize that, and basically gets larger, but not at every step, right? So if we're jumping from 3 to 2 and then back to 3. The adjusted R squared basically starts large and decreases, though you can see how slow the decrease is, right? 0.44, numbers in the 0.44 range sort of stick around for a long time before they get sizably worse. We don't actually get any adjusted R squares that are negative, though that would be a possibility. And then R squared values are different because they're not penalized, whereas all the other ones are penalized. All right, size is how many variables are in the model. And this top model has 2, and we're not counting the intercept. The intercept is in every model. What we're counting is how many of the X variables. So we have weight and year age. That is, for this data set, the best model in terms of BIC. And it's basically the best model in terms of the others as well. It is for CP. For adjusted R squared, there are some adjusted R squareds that are larger. Okay, we've got a couple 0.46s and a 0.45. But it's, it's sort of in the ballpark of 0.44, 0.46. In terms of the proportion of variability explained, these are not large differences, 2 or 3%. So, and the ones, the ones indicate that those are the variables that are in the model. Zeros indicate that those variables are not in the model. And so it gives you a sense of what those best models are. And so one strategy you can use is you can take a look at, say, maybe the top. So in this case, I would actually look at, for the BIC value, I've got -14, -12.6, and then 10, almost 11. So it sort of takes a big jump there. There's a bunch of values at 10, 9. So, really I would sort of restrict my attention probably to these top two because their BIC values are fairly close. And then there's a big jump of two units. And one thing that these two models are pretty similar, right? So the first model had weight and year age, and the second model has weight, year age, and the chin, the skin fold measurement for your chin. And how does it improve the R squared? Well, it increases it by about 3% from 0.47 to 0.50. And they both basically have the same CP statistics. So I might just conclude that the top one is better because it's that much simpler and we're not losing that much predictive ability in terms of R squared, and go with that one. Assuming, of course, that all the models fit looks good with the residuals and so on. But this output gives you a lot of information in one table. I really like this for looking at very complex models where there's tons of predictors, possible predictor variables, and having a sense of, I want, if your situation is I want an idea of what good candidate models are, here's a way to look at a bunch of good candidate models all together and see that most of them probably have a lot in common. In fact, if we just look at these right here, right? Say we look at the top 7. So most of these have, they have 2 to 4 variables in the model. They all have year age. They all have weight. How do they differ? One of them has a chin fold measurement, the chin skin fold measurement. One uses the forearm. One uses the calf. And what's the difference in R squared? Not that much. They differ sort of around 1%. So it seems that if you want to improve a little bit, choose one of the skin fold measurements. Okay? Then, if you don't do one of the skin fold measurements, you can put height in there. That's sort of a painless measurement to take. Or the pulse rate. Or if you're going to include the chin fold measurement, you can also include height. But at that point, you've got 4 variables, and you're not really doing that much better in terms of R squared. So this tells me, the summary for this tells me that I need weight, I need year age. And if I was conducting a study, for example, some sort of diagnostic, I was in a clinic, and I was in a clinic environment, and I wanted a simple model to help predict their blood pressure. This I could do by asking 2 simple questions, basically. Ask them how old they are and how long they've lived at lower altitude. That gives me year age, and I'll ask them their weight. With those 2 questions, I get about 50% predictive ability, and I don't do that much better by taking out the calipers and measuring their skin, or taking their pulse rate, or measuring their height on a scale, even though their height's not too difficult to measure. So my the height has 0.47 for R squared. 0.47 is already up here. So we're not really gaining anything with height. So I asked three simple questions, and I've got as good a model as I can, at least with this set of variables. All right. All right. So here's a write-up of some of the things that I've just discussed. Okay. And discussed all that. Yep. Said a whole bunch of stuff. All right. Let's look at one more example. Oxygen uptake. An experiment was conducted to model oxygen uptake. That's going to be the O2 up is the response variable in milligrams of oxygen per minute from 5 chemical measurements. So what the biological oxygen demand is, the total, everyone say it with me, Kaldal nitrogen maybe, the total solids, total volatile solids, which is a component of TS, and the chemical oxygen demand, COD. Each are measured in milligrams per liter. So the data were collected on samples of dairy wastes kept in suspension in water in a laboratory for 220 days. Ooh, That's some sort of experiment, I guess, for someone else to conduct, not me. All observations were on the same sample over time. Okay, so we have one sample, and we're taking what's called repeated measurements. So you're going to collect this maybe every week or so. We'll see in a moment how frequently this is measured. We desire an equation relating what the O2 oxygen uptake is related to the other variables. The goal is to find variables that should be further studied with eventual goal of developing a prediction model. And for some reason, day should not be considered as a predictor in this particular study. Maybe they want to be able to observe a sample of dairy waste with unknown history. So we don't know how long it's been sitting somewhere, suspended in water, and we want to just measure these other variables and then predict what the oxygen uptake is for that sample. All right, so researchers believe that the predictor variables are more likely to be linearly related to the log of the oxygen uptake rather than the variable in its natural units. So we're going to include the log in the data set, and we're going to start off by plotting the data and see what the relationships are. So here is the data set. Let me go ahead and click on the data and take a look. Okay, so we've got about 20 observations or so, and we can see the day, it's basically measured roughly once a week. And if we look at the oxygen uptake, we can see it's high at the beginning and it basically trickles down to 0. And some of the other variables start high and go low, while others basically stay roughly constant. Hey, what do you know? I've included the data here as well. So the plots, let's take a look at the plots. So right away, your eye fixates on this one point that seems wildly different. This was the first observation. Let me page back up for a moment. And we can see the log, or see the O2 uptake for that first, on day 0, is extremely high. So we may want to, we want to make sure we keep that point in mind. Is there anything else as we look here that seems a little bit unusual? Maybe not. BOD for that last day seems pretty low, though it's, and that last day was, the duration between the 19th and the 20th measurement was 50 days, almost 2 weeks. So there's a gap of time there that's unusually wide. In fact, these last few days sort of much longer apart, whereas everything else is roughly weeks apart, or 1 week apart. Okay, I'll page back down. Okay, so it's possible we want to not include day 0, since maybe we're measuring residual oxygen and not oxygen that's, part of the process. What else do we see? We see some curve relationship here, so that's sort of interesting. Maybe a curved relationship there. It definitely seems to be the spread seems to be related to the mean of oxygen uptake. So when all the values are small, there's very little variability, and as the variables get larger, there seems to be more variability. So that log transformation is looking like a good idea at this point. So let's go ahead and take that log transformation. And here we've created a variable log up, and that's what we're plotting. So same plots as before. On the log scale, this is looking a bit better, though maybe this is a suggestion here of a quadratic relationship. Sort of linear here, maybe linear or curved. Boy, this point is really unusual, TVS. What's that TVS really low value? Let me scroll up for a moment. TVS is this variable. and this day here is particularly low. Okay, so there's definitely some unusual, page back down, unusual measurements here, and we want to worry about those when we're looking at the residual plots. And I hope that I've also included some added variable plots here, because it will be interesting to see whether there's influential or unusual observations in that multivariate space. All right, so let's use that function I wrote to give us all that output all at once. So here I've put in, with the log of the oxygen uptake as the response variable, I've put in all the other variables as main effects. Now it's possible at this point that we could actually consider interactions and quadratic terms because we have those skills with us. But in terms of just focusing on the simple goal of fitting this model, let's just do sort of a simple regression where we just have main effects. So I'm looking at the best 3 models for each model size. And it's an unfortunate break to have the headers up here, but I think we can live with it. It is sorted by BIC, so we have negative 21.8, negative 20.7, negative 19, 19, and maybe it's sort of about there where I would sort of stop my interest, maybe about these first 4. And let's see what they've got in common. So the R-squared values are all sort of around 80%, about 78% or so, 79%. Adjusted R-squareds are all very similar. The CP statistic is clearly suggesting to me this first one, or maybe second one. And this top model is actually this only has 2 predictors. So what are those? We've got COD and TS. What's the next best model? It has COD, TS, and TKN. What's the third best model? It also has those 2 variables, but COD instead. What's the next best? It always has those 2 and BOD. So it's clear to me that these 2 variables, COD and TS, are important. And now we can ask, what do we gain by adding a third variable, or even a 4th variable in this case? As I look across at R-squared values and CP statistics, I don't see big advantages. So as long as the residual plots are looking pretty good for this first model, that's sort of a clear winner to me. And basically the thing I will have learned is that these 2 variables are primarily of importance in this model. But so let's take a look. So this is the model with those 2 variables, TS and COD. We see that they're both significant together. And I've got some residual plots. Good. So that first observation is definitely influential. It's influential because it's unusual. Observation 20 is also a bit unusual. That was that last day, which was measured almost 2 months after the measurement before it. So it could make sense here to worry about these 2 points and maybe exclude them from the analysis. They're these 2 points right here. Fortunately, they sort of balance themselves out in terms of what the regression line would do. So they both shift the regression line up. So right, without this point and without this point, this regression line, what's indicated by the 0 line, would be lower, but it would basically still have the same slope. So I'm not feeling too worried about the regression model changing very much in this case. We definitely see those 2 large residuals out here in the normality plot. Otherwise, these residuals look pretty straight. When we look at the added variable plots, same thing. These 2 numbers, 1 and 20, are ones that really stand out. Everything else looks pretty good. sort of surprisingly to me, given the relationships that we saw in the original scatter plots. So if we redo the analysis excluding those two unusual points, I'm just going to make a new data set, oxygen 2, and I'm going to subtract or remove the first and 20th index to remove those two unusual points. I'll go ahead and do best subset selection again, and now look at this, BIC 31, negative 31, BIC negative 28. So you have about a 3-point difference there. That's a huge difference. So that's suggesting to me that the clear winner is, again, that same model, and we're not really going to gain very much by increasing the complexity. The adjusted R squared goes down when you add that complexity, and the R squared itself is basically staying the same at 89%. So we'll take a look at the diagnostics. I'm not too worried about the model coefficients here. R squared is 89%. What did we have before, by the way? Sorry for jumping around. 78. So there was a lot of unexplained variability from those two unusual points. Okay, so that was 89%. Let me scroll down and we'll take a look at the residual plots. Yeah, this looks pretty beautiful. No really highly influential observation. These residuals, all these residual plots look really good. There's, points 3 and 4 are a little more influential because they have higher leverage, but everything looks pretty good. The QQ plot looks about as good as it can get. The added variable plots, same thing. We see this positive relationship in both cases, and we don't see any single point that's really speaking to the relationships we're seeing. So this is looking really good. Here's our final model. Plug in those coefficients from the regression. Looks like there's fairly small effects in terms of the units, but that's really just about the unit of the variables, right? We're predicting the log on the log scale, and TS and COD are on whatever units they are. So even though there's lots of zeros here, it doesn't mean that they're not important. They're clearly important from the modeling exercise. And that's the end of Chapter 10.